Hi everyone. In this lecture, we're going to be talking about energy. Now, there are several lectures that are here on the site that deal with specific types of energy that we have seen already. We've seen sound, we've seen electricity, we've seen light, we've seen heat. All of those are forms of energy. So this particular lecture deals with energy in general and some of the transformations that energy has, and then it's going to focus mostly on mechanical energy. So as we talk about Newton and his laws. So let's take a look. So what exactly is energy? Energy is the ability to do work. This is the way that we in physics will define energy. It is the ability to do work. So that's an important thing to remember. Typically, energy is going to either be potential or kinetic. And this is regardless of what type of energy we're talking about. We could talk about chemical energy and be chemical energy of potential energy that's chemical, like in a battery. We could have potential energy gravity, due to gravity by position. If I have a ball that's hanging over my head, I could drop that, and when I drop it, it becomes kinetic energy. So you have potential energy due to position, and then kinetic energy, which is the energy of motion. Now, if you'll recall, when we started talking about matter, there was a law of conservation of matter, and that has to do with when we're going through chemical changes. If there's chemical changes, you know that you're going to have the same amount of matter at the end that you started with at the beginning. Well, in reality, that law really is the law of conservation of energy and matter. Because energy is conserved as well. Energy is not created or destroyed. It's only changed form when we're talking about an entire system. Now, please try to remember though that this is when we're talking about ecology. Energy flows through an ecosystem because it comes into the ecosystem. There's a constant input of energy from the sun, and then there's a constant outflow of energy as well because energy is constantly being lost to the atmosphere. Now, that doesn't mean that energy is being created. It doesn't mean that energy is being destroyed, because there, when we look at the entire system, we're looking at something larger than just the Earth, larger than just our solar system and whatnot like that, because energy is coming in, but energy is also flowing out. So, the law of conservation of energy is that energy only changes form. It is not created or destroyed. So, and again, all of the links that I've put onto here in these recordings, if you take a look at the non-recorded slide decks for each one of these, which are also here on this website, then what you're going to find are that the links are active there. So, forms of energy. Like I said, this lecture is going to primarily deal with mechanical energy. Mechanical energy is energy that having to do with things moving, parts, machinery, the simple machines, etc. This kinetic energy plus, and this is also including sound and also potential, because mechanical energy, you could have chemical energy that's potential, you could have mechanical energy that's potential. That chemical energy could become mechanical energy. Chemical energy, which is energy that's involved in chemical reactions. You could have, whenever a chemical reaction takes place, if energy might be released during that chemical reaction. If it is an exothermic reaction, if that takes place, then you have moved from you've moved from a higher energy level to a lower energy level, and as a result, that energy is given off, and so you get energy out of that particular reaction. So when we started, we had chemical potential energy. Radiant energy, which is electromagnetic, and we've talked about this. This is light and all of the forms of radiation, going, from gamma rays, cosmic rays, radio, radar, which is using radio waves, all of the visible light spectrum, etc. So this would be electromagnetic energy, and the visible light, remember, is only a small part of that. And also radiant energy includes heat, and we, in a previous lecture, talked about the different ways that heat can be moved from one place to another. Remember, convection, conduction, and radiation. We will talk about electrical energy, and we've talked about electricity already and setting up circuits and whatnot like that. Remember, what is electrical energy? Electrical current is the movement of electrons. Then we also had static electricity, which happens when you have an imbalance of electrons. Then nuclear energy, which is the energy that is released according to that wonderful equation equals mc squared whenever we have fission or fusion going on with a nucleus. Whenever there's a nuclear change, nucleus, if there's a change in an atom's nucleus, then we will have nuclear energy that is being produced, whether it be fission, where you have one atom being split apart into multiple atoms, or if you have multiple atoms being fused together to make one atom. In both cases, part of the mass that's involved is transformed directly into energy by E equals mc squared, and that is nuclear energy. So here's some examples of some changes that energy can go through. In chemical energy, by oxidation, chemical energy can be chemical potential energy can become some other form of energy. It might end up being radiant energy. Actually, when chemical energy is oxidized, it can be changed into another form of chemical energy. We see that in cellular respiration. Chemical energy can be changed into heat. We see this whenever we put fuel in any type of motor. You put fuel into that system, and part of the energy that's contained within the fuel, the chemical energy, is changed into heat. If it's a car, a lot of that energy is released as heat. If it's supposed to be released as heat, like you have some sort of a chemical heater, like a butane heater or something like that, then you're getting heat energy. That could also be transformed into mechanical energy. Chemical energy is daily, we see this transformed into mechanical energy when you put gasoline into your automobile, and then ultimately that is used to drive the car forward. So that's changed into mechanical energy. Chemical energy in batteries is often transformed into mechanical energy when you have, say, a radio-controlled car or vehicle of some sort. Electrical energy can be transformed into mechanical energy. Typically, the chemical energy of a battery is transformed into electrical energy, which runs an electric motor, which then we get mechanical energy out of that. So the whole point of this diagram is to show you that there are so many different ways that energy can be transformed from one form to another: chemical, radiant, mechanical, nuclear, electrical. So we get a lot of different energy forms from all of the other energy forms. You know, the energy that's powering your house right now could be chemical, it could have started as mechanical, it could have started as nuclear, depending on where you live. Some terms that we need to know when it comes to energy. A force. Okay, so what is a force? Besides, feel the force, Luke. I know. Yeah, dad joke. A force is a push or a pull capable of changing an object's state of motion. So anytime something pushes or pulls on something else, we refer to that as a force. Work. So what is work? It's that place that you go to every day, right? So in physics terms, work is when we apply a force over a distance. So if I were to push an object a meter on the floor, I have done some work. So work literally is a force applied over a distance. So then we have power. Well, here's the equation for work. Work is equal to force times distance. Okay, work is equal to force times distance. So there's your first formula for this particular unit. Power is the rate at which work is done. In other words, it is the work divided by time. So power is equal to work divided by time. How much work was done divided by how much time. And power is in watts. So you will see force in newtons, power is in watts. So let's move along. Simple machines. Simple machines are the simplest of way that you can essentially multiply the amount of force, or get more output from the force that you're putting into something. So let's take a look. Simple machines help us convert from one form of energy to another. It multiplies your force. So it could help you lift a heavy object. So for instance, if you're using a pulley system to lift something to a higher level, then a pulley is a simple machine, and that allows you to multiply the force by using just the same force. If I were trying to just lift it straight up, then I may not be able to do it. But by using a pulley system, I can multiply the amount of force that I'm using in order to do that work. I could multiply movement. So you could help lift an object higher, gain distance without losing the force. So you can raise an object higher without using more force. So the simple machines: a lever, a pulley, a wheel, an axle, wedge, a screw, or an inclined plane. So all of the mechanical devices that we use are combinations of these. They're combinations of these simple machines. So let's take a look at them. So here are our simple machines: wheel and axle, a lever. Now there are actually three different classes of lever. You have a first class lever, which is what is shown here. You have a second class lever and a third class lever. An inclined plane, so if I need to lift something up to a higher level, I can literally push it up the plane, which allows me to get it up to it's a ramp. So it allows me to get what I need up to a higher level without actually having to lift it. A wedge, in order to split things apart, a screw, and pulley. So these are the 6 simple machines. If you are teaching a physical science course of any type at any level, you are going to have to teach about the simple machines. And there are so many ways that you can incorporate simple machines into lessons. There's so many ways that the simple machines can be used. Students can use the simple machines in a lab activity. So some of the terms that we need to use for simple machines: effort, which is the amount of force that's applied; resistance, which is the force opposing the motion. Typically you'll have things like friction, gravity. Input is the work that is applied. Output is the work that's produced. So remember, work is force applied over a distance. So input is the work that's applied. How much force over what distance am I applying to something? And the output is how much work over what distance was actually produced. Now, one of the things that I have done with students in the past is I make them create a complex machine with multiple simple machines, and they have to calculate at the end how much work was actually done by their machine. Well, how much work was done, how much force over what distance was applied at the end of their machine. Efficiency. This is the ratio of output to input. Okay, how much work was produced divided by how much work was applied. Output is going to always be less than the input because some energy that you put in is going to be lost due to friction. So machines are never 100% efficient. Okay, machines will never be 100% efficient. So the mechanical advantage is the ratio of resistance to effort. Okay, how much force was resisting the motion to how much force was being applied, and that would be our mechanical advantage. And when you take a look at this particular slide deck, when you take a look at this slide deck that's not recorded, go ahead and take a look at this YouTube video. I think you'll find it humorous. It's a group called Ready Set Go, and they're showing a Rube Goldberg machine, which is really incredible. All right, so let's take a look at Newton's laws of motion, because if you're teaching physical science and you're talking about energy, you've got to deal with the laws of motion. So the first law of motion is the law of inertia. Inertia states that any object at rest or in motion will stay in uniform motion or at rest unless it's acted on by an outside force. So unless it's acted on by an external force, an unbalanced force, the object will continue in the same line of motion or it will continue at rest. Okay, you've probably all seen this. The nice trick of yanking a tablecloth off of a table while all of the dishes and everything remain on the table. If you do that quickly enough, then the inertia of all of the items on the table should keep them on the table. Now, I wouldn't suggest doing this on a table on your parents' table with the good china out, because it takes an awful lot of practice to do that. So inertia resists any change in motion, and inertia is a property of matter. Inertia resists any change in motion. So, for instance, when you get on a bus and you're standing still and the bus starts to move, all the people on the bus are going to pull backwards, and that's because of the fact that you are resisting motion. And so you are at rest and you're only going to be in motion because the bus is moving. And so that as that bus moves, then you will start to move backwards. If the bus is moving in a straight line and then the bus turns, everybody turns. Okay, that's because, again, you were moving in a straight line, and so now there's an unbalanced force that is as the bus turns, and so that unbalanced force causes a change in the motion. And so everybody's inertia wants to keep them moving in the same straight line, and so what happens is everybody tilts. So that's Newton's first law of motion, inertia. The second law of motion is that force causes acceleration. This is the law that you've probably seen on many occasions, and I'm going to see if I can get, there we go. F is equal to ma. Force is equal to mass times acceleration. So what does this actually mean for us? If we take a look at all the parts, our units, force is always going to be in a unit called newtons. Yes, named after Isaac Newton. So force is always going to be in newtons, mass, grams, acceleration, meters per second squared. So the more force you apply to something, to a mass, the more acceleration it's going to be. So it's not so, as you apply a force to something, it's not just going to move, it's going to accelerate. If I have a toy car in front of me and I push it, as long as I'm applying a force to it, it is not only moving, it is going to accelerate, and it will, unless that force remains constant for a while. As that force remains constant, then it will be at constant motion. But as soon as I stop applying that force, then things like friction and air resistance, that's all going to act on it, and it will start to slow down. So force is equal to mass times acceleration. So acceleration is the change in velocity per unit time. Change in velocity per unit time. So for instance, if I'm accelerating at 5 meters per second squared, that means for every second I'm going 5 meters per second faster. So at the very beginning I might be going 0 meters per second. Then after the first second I'm going 5 meters per second squared. After the second second I'm going 10 meters per second squared, etc. So acceleration means that not only am I moving, but how fast I'm moving is increasing. So this is a change in velocity that results in a change in speed, a direction, combination. Okay, velocity velocity describes both the speed and direction of a moving object. So typically when we talk about speed, we're only talking about how fast something is moving. When we talk about velocity, we're also talking about a direction. So a change in velocity is a change in speed, direction of travel, or both. Okay? So whenever something accelerates, it is moving, how fast it's moving is actually changing each second. And that's what this law means. As I apply a force to a mass, it not only will move, but it will accelerate. So acceleration is equal to force divided by mass. If you need to change that. Here's some examples of Newton's second law. If something has more mass, it will have less acceleration. Let's see if we can get that. There we go. If something has more mass, it will have less acceleration if the same force is applied. So let's take a look at this bicycler over here. Obviously, he's applying force in order to ride forward, so the force is applying, moving it forward. There's friction between the tires and the ground. There's air resistance between the bicycle and the air pushing it. So air and friction are pushing it backwards. Force is applied, moving it forward. If those are balanced, then the bicycle is simply going to move forward at a constant velocity. But if you apply more force so that you overcome those forces that are pushing you backwards, then you will accelerate. If the bicycle is heavier and you apply the same force, the acceleration will be less. If you apply more force, then you will move forward faster. If the bicycle is lighter, has less mass, then you apply the same force, then you will accelerate more rapidly. So the rate of acceleration equals the change in velocity over time. So force is equal to mass times acceleration. This also applies to, you've often heard people say that mass and weight are not the same thing. And this is true. Mass and weight are not the same thing. Okay? Mass is how much material, how much substance, how much matter makes you up or makes something up. And weight is how much gravity actually pulls on that mass. Okay, so mass is the quantity of substance in something, and weight is how much the force of gravity acts on that mass. So really, when you describe somebody's weight being in kilograms or something like that, you're missing something, and that is actually the acceleration due to gravity, which is 9.8 meters per second squared. So really, when you talk about the weight of something in metrics, you should be talking about newtons, which would be force. So it's how much ever your mass is multiplied by 9.8 meters per second squared. Well, the reason that we don't, and why that's more of an academic conversation than a reality conversation, is because gravity is going to act on you exactly the same way all the time. As long as we're not leaving the planet, gravitational acceleration is going to be 9.8 meters per second squared, because we measure that from the center of the Earth. Now, you may have slight differences. The force of gravity may be slightly different, albeit very unlikely to be measured with most common machinery, common material, at the top of Mount Everest and that sort of thing. So you're going to get so little variation in gravitational acceleration unless you leave the planet, then it's only an academic conversation. But yes, mass and weight are different, but from a reality standpoint, we're simply taking off the times 9.8 meters per second squared because it would be there for everything that we do. So it's just as easy for us to talk about something having a mass of 3 kilograms and letting it go at that. We don't need to say it's 3 kilograms times 9.8 meters per second squared and give it in newtons. So when you give your weight in pounds, however, that is giving it in force. So when we talk about the pounds of something, you are talking about how much mass something has multiplied by gravitational acceleration, and that's giving you pounds. So whenever we talk about kilograms, obviously that is a measure of mass. So if you went to the moon, and this is a classic example, your mass would not be your mass would be exactly the same, but your weight would be different because the gravitational acceleration on the moon is different. So it's probably easier for us to mostly just talk about mass because but for all intents and purposes, we're not going to see much difference because we're not planning on leaving. You're not going to be leaving the planet to teach a course, and so. But this is just so that you know that there is in fact a difference between these things. All right, so the third law of motion relates to forces between objects, and this is whenever two objects interact, the force exerted on one object is equal in size and opposite in direction to the force exerted on the other object. Equal and opposite forces. Okay, so when something exerts a force on something, an equal and opposite forces will be acted upon that for the first thing. So for every action, there's an equal and opposite reaction. Thank goodness, otherwise rockets wouldn't work, right? So think about being on ice skates. If you're on ice skates and you're standing palm to palm with someone else and you both push off, you're both going to be going in opposite directions. Or even if one of you pushes, you're both going to be moving off in opposite directions. So whenever there's whenever there's a force, there's always going to be an equal and opposite force. So every action, there's an equal and opposite reaction. In a rocket, you get combustion that thrusts hot gases out of one end of the rocket, and what does that do? It forces the rocket to go in the opposite direction. So rockets fire because of Newton's third law of motion. All right? So Newton's laws of motion, we had inertia. Force is equal to mass times acceleration, and for every action there's an equal and opposite reaction. One of the things that I would always suggest if you're teaching that concept to students, show them an example of each one, but then make them come up with an example for each one and then demonstrate that to the class. That really shows that they have a good understanding of what that law of motion is. All right, so Newton's law of gravitation states that there is an attractive force between all masses. Every object in the universe pulls on every other object in the universe. And this is proportional to the masses of the two objects that are pulling on each other, the product of those masses. And it is inversely proportional to the distance that separates two things, or the distance squared. As two things move apart, obviously their gravitational pull is going to be less. Now, let's put that into perspective. The Earth is pulling on me. Okay? The Earth will continue to pull on me regardless of where I am on the surface of the Earth if we're measuring it from the center of the Earth, because I'm not appreciably changing my distance. If I'm staying on the planet, even if I climb to the highest point at the top of Mount Everest, the distance between me and the center of the Earth has not appreciably changed. Therefore, the gravitational pull between me and the Earth is not going to be that much different. The Earth and the Moon have a gravitational pull on one another. That's why the Moon stays in orbit. That's why the Moon has an effect on things like our tides and whatnot like that, because the two things are pulling on each other. This also explains why gravitational acceleration on Earth is 9.8 meters per second squared, because no matter where we are on the surface of the Earth, you're not that far, you're not changing the distance really between you and the center of the Earth, and so it's going to remain 9.8 meters per second squared for the most part. Provides centripetal force for the orbital motion. Okay, when the Moon orbits the Earth, because the Moon is constantly being pulled to the Earth, but it's also falling. So it's falling around the Earth, it's falling towards the Earth, but it's also in motion. And so as it moves, the ground moves away from it underneath, and so it stays in orbit. And that's how whenever, satellites and everything are placed into orbit, we have this, because a satellite is going to want to fall because of gravitation, but as it's moving forward, the ground beneath it is also moving away from it, so the thing essentially falls around the Earth. That's orbit. If something happened in that orbit were shortened, then the object would slowly fall and hit the Earth's surface. So two objects, mass 1 and mass 2, are going to pull on each other, and the force that they exert on each other is going to be proportional to the square of the distance, how far they are apart. And so this is what I was saying. The moon, because of inertia, should be moving in a straight line, but the Earth's gravitational pull is pulling it towards the Earth. So as it tries to fall in a straight line, follow a straight pathway, the Earth's gravitational pull is pulling it. And so what it ends up doing is it essentially falls around the Earth continuously. So the moon is in orbit. That's what orbit means. So here are some study websites on simple machines, energy, etc. Again, these links are live when you take a look at the unrecorded version of this slide deck. And with that, we'll bring this conversation of energy to a close.